What's up, everybody? Welcome to Unit 8 of General Chemistry, a unit on chemical bonds. This will be looking at parts of chapters 7 and 8 in your textbook. And the reason I say parts of chapters 7 and 8 is there is a section in each of those chapters that has to do with nomenclature and formula writing, and we did that way back in Unit 2. So I've combined the two major bonding chapters of the book, one on ionic, one on covalent, and kind of picked out the pieces that don't involve the naming and writing, and moved forward from there. So we're going to go on now, and we're going to spend the next 15 or 20 minutes talking about different types of chemical bonds. So, without further ado, here we go. We are going to start by talking about ionic bonds and ion formation. And the whole thing about ionic bonds is it comes back to like talking about just bonds in general. And so, if we looked at the question, what is a chemical bond? A chemical bond is the force that holds any two atoms together. So bonds exist between two atoms. We usually look at them as between two atoms, even if there are more atoms involved. And when we start talking about ionic bonds, it gets even a little crazier. So bond formation, at least in terms of ionic bonds, and ionic bonds involve ions. You can see the word ion right at the start here of ionic. An ionic bond is the attraction between, or any bond is the attraction between the nucleus of one atom and the negative electrons of another. And for ionic bonds, we are looking at that attraction between positive and negative ions. See the word ions there, and obviously I mentioned ions as an ionic bond as well. Ions are atoms, either monatomic, and monatomic, of course, means one atom, and I just spelled atom wrong. Or groups of atoms, which are called polyatomic, poly meaning many atoms. So we have either monatomic or polyatomic ions that have either a positive charge, which means that there are less electrons than protons, or has a negative charge, which is more electrons than protons. And we look at this in terms of electrons because we know the number of protons stays the same. It is electrons that are getting moved around. All right, you cannot change the number of protons of any atom without changing what element you have. So it's only the electrons that are the currency of bonds. Well, if we look at the different types of ions that are out there, we have cations. All right, we can think of these as positively charged ions. I like to think of them in terms of cats. I'm a cat person. Cats have been shown to help enrich the lives of their owners, especially elderly owners, because you pet them and they purr and they make you feel good, release those good endorphins in your brain. All right, so cats are a positive influence on people, and they form when an atom loses one or more electrons, and typically we're speaking of valence electrons. It gets a little confusing when we start dealing with D and F electrons because they're not technically valence, because their energy level is lower than the valence energy level. But for the most part, we're talking about these valence electrons, and we can look at it in terms of the two major types of elements and how they react. So for metals are reactive because they lose valence electrons easily. All right, and if we really think about how they lose them easily because they have low ionization energies because they are large. And if we take a look at the little diagram here, we have sodium. There's the sodium nucleus, the little red dots that my laser pointer's over right now. Each of the blue dots is an electron. You can see there are 11 blue dots with no charge. This is a standard sodium atom. Well, you can see this second ring is totally full of its 8 electrons. It has a complete octet. So sodium happily and quite easily loses this single lone electron that's out there, all right, and it becomes a sodium ion, where now look how much it shrank. That whole third energy level went away. There are now more protons than electrons because our electron number decreased, and we have a positive 1 charge. And now we have what is known as a sodium ion, or a sodium cation, because it's positively charged. The other major type of ion is the anion, which sounds kind of like an ant. All right, and I don't mean like your father or mother's sister or sister-in-law. I mean like an ant that comes and steals food at your picnic. We've all seen the cartoons where the ants come in and then they take all the food away. That's what I'm talking about here. That's kind of a negative situation, watching your loaf of bread get carried away by a bunch of cartoon ants that may or may not be singing a catchy little song. This forms when we have an ion gaining valence electrons. All right, and the big part of here is it's that gain of electrons. All right, it could gain 1, it could gain more than 1, and we see these in the names because they end in "ide." So if you think back to when we did nomenclature, we had to change the ending of those nonmetals. We had to go oxygen became oxide, chlorine became chloride, sulfur became sulfide. We had all that fun little switching of the ending. Well, this "ide" means we're dealing with an anion or a negative ion. And this happens because the nonmetals gain electrons so that they can get that valence electron number of 8. And a little example I have here, we have chlorine. Chlorine has a nucleus. There's 17 protons in it because its atomic number is 17. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 total electrons. No charge because they're the same. But there's this gap right here in this third shell that with 1 more electron, it could be full. And so if chlorine gains that 1 electron, like it does here, we now have 1 more electron, or 18 total electrons. And so there are now more electrons than protons, which means we have a -1 overall charge, or a 1 negative overall charge. And that's because electrons are negative, protons are positive. Well, how does all this play a role? It plays a role in ionic bonds. And ionic bonds come from electrostatic force holding charged particles together. And it's actually holding oppositely charged particles together. So it's holding anions and cations together. The positive cation and the negative anion are attracted to each other, a lot like you would see the negative and positive end of a magnet, or 2 different magnets attracted to each other. Ionic compounds are compounds that contain ionic bonds. That's pretty straightforward, nothing special there. And for the most part, in binary ionic compounds, binary means there are 2 elements, not necessarily 2 atoms, but 2 elements. We generally see a metallic cation, so a metallic positive ion, and a non-metallic anion. Sodium chloride and iron 3 oxide, which is also known as rust, are big examples of this. The overall charge equals 0, so that means the number of positive charges equal the number of negative charges. If you think back to when we did writing on these, we would crisscross applesauce those charges. That's to get this balancing of the charge. And in the little picture here, I have sodium, which I saw earlier. All right, I had a little picture of sodium. Its electrons I'm representing by little x's. Chlorine, I'm representing the electrons by little dots. What you can see when sodium became a sodium ion, it lost that little x, and that little x just happened to pick up or be picked up by chlorine to fulfill its outer ring. So now we have a sodium with an extra charge here. We have a sodium with one less negative charge here. We have chlorine with one more negative charge here. The positive and negative attract each other, and we get what is called an ionic bond, which is just this positive being attracted to this negative. There are a ton of different ionic compounds out there. Just take a metal from your periodic table and take a non-metal from your periodic table, crisscross applesauce those charges, and you can see an ionic compound. You could have an ionic compound that contains those polyatomic ions, which are usually found in lists. For you guys who recognize my voice as your real teacher and not just some crazy YouTube dude, you have a list of these polyatomic ions on the back of your periodic table, right? So you can crisscross applesauce those charges. A lot of different polyatomic ions or different ionic compounds. Anyway, the physical structure of these, all ionic compounds share a couple of things in common, all right? The cation ions and the anions, the positive and negative ions, exist in a ratio. And the ratio is determined by the number of electrons transferred. So a sodium to chlorine in sodium chloride, NaCl, or even better, let me use my example here, NaF, there's one sodium for every one fluorine because one electron is transferred. And magnesium oxide, MgO, magnesium is given 2 electrons to the oxygen. Right? If I went more complex and I did sodium with oxygen, there would be 2 sodiums for every 1 oxygen, and that's just to balance out those charges. Ionic compounds exist as a crystalline lattice, which means there is a 3-dimensional arrangement of particles in some form of geometry, and this can take a cubic geometry like we would see in table salt. It could take a hexagonal geometry as we see in the mineral fluorite, and so we can get different shapes from these different ionic compounds. And really what we're seeing is that each cation is surrounded by anions. All right, so all the positives are surrounded by the negatives, and all the negatives, or the anions, are surrounded by the cations. All right, so we can see those two things. Physically speaking, what we see is that these are dependent on how strongly the particles are attracted to each other. All right, so the stronger the attraction between the positive and negative charge, the stronger the physical properties. If we were to really be general here, all right, you can easily find things that go against these trends, but the major trends, all right, is think of table salt. All right, there's high melting and boiling points. All right, you guys have probably never seen melted table salt, which is sodium chloride. Probably never seen it because it has a melting point of hundreds, if not over 1,000 degrees Fahrenheit. There is very low conductivity as a solid. All right, salt does not conduct electricity well in its solid form. However, if you were to melt it, it becomes a great conductor of electricity because now those ions can move a little bit and allow the electricity to jump from the different charged particles. Whereas when they're stuck in the lattice, remember, each positive surrounded by all negatives, so the electricity cannot jump between the positive ions. The one other thing I want to talk about here for the last couple of slides is what happens when we don't have ionic bonds. What if we have just metals? Samples of just metals have their own interesting interactions called metallic bonds. Metallic bonds are known as the sea of electrons. All right, where the valence electrons are spread out across the entire lattice of the metal. All right, they're not exactly shared, as they are more like community electrons. This is like chemical communism, maybe, right? Where you have they're all the electrons are the valence electrons of all the atoms at once. And so essentially all those valence electrons belong to all of the atoms in the substance. And what this leads to is you got all the positive nuclei and then this like sea of electron that's like in one giant electron cloud combination of orbitals that just is spread out among all the atoms in the sample. And that leads to like very cool and nifty properties of metals that we don't really get to see anywhere else. Some of those cool and nifty properties that we were talking about involves melting and boiling points. Depending on the metals have moderately high melting points. They usually don't tend to be as high as ionic compounds, but they tend to be higher than non-metal melting and boiling points and covalent compound melting and boiling. So that's why I'm saying moderately high. But the really cool things that metals can do is because of their structure and these metallic bonds, all right, it allows the atoms to kind of be moved in interesting ways. So we can hammer out metals into sheets, which is called malleability. We have ductility, which means we can draw them into wires. If you've ever opened up like the cord that something gets plugged into the wall, or if your iPad cable, charging cable frays, or that happens with like some wired headphones, something you can see the copper wires. And they are very durable. Metals tend to have a high durability because they have strong attractions between their ions. And the main reason for this, again, is because those electrons are delocalized. They're communal electrons, essentially. Because there are this sea of electrons, all right, and think of like each electron being like a molecule of water in a sea, those electrons can free flowly throughout that sea. Like the water can like move freely throughout the sea. And so that allows really good conductivity, and metals end up being really good transfers of both electrical conductivity and thermal conductivity, or heat. And D-block electrons, which is most of the metals are right there in that thick D-block in the middle of the periodic table. More D-block or electrons tend to increase the hardness and strength of many metals. It's not always the case. You do have the copper, silver, gold family there, column 11 or 11b, depending on your periodic table, that are kind of soft. But you will see like really hard elements in there like nickel and iron and chromium and titanium are inside the D block and add to some of that strength and stability. Or strength and hardness is probably the better word than stability. Finally, we have learned to do fancy things with metals, and that is we've had them form alloys, which is a mixture of elements that have metallic properties. We usually have to melt the metals at really high temperatures and mix them together in their liquid state. You can't just take like a chunk of iron and a chunk of chromium and beat them together between your hands. You're not really doing much except maybe crushing a finger if it accidentally slips in between the two hard metals. You would heat them up to really high temperatures and then mix them that way. There are two major categories of alloys. There's the substitutional alloys, which is where we can replace one element with a number. All right, if we replace some iron atoms with chromium or nickel, we get what is called stainless steel. And there's a whole common list of alloys in your textbook on page 228. There are also alloys called interstitial alloys, and that's when we take small holes in a metallic crystal and we fill these small holes with smaller atoms. So the substitutional ones, and I didn't really highlight this, so in substitutional ones we actually go in, all right, and we replace original metallic solids. We go and replace the original metal with other metals that are of a similar atomic size. Whereas in interstitial alloys, we go in and we fill the small holes between atoms with, or the small holes between the metallic atoms in the metallic crystal, we fill those with smaller atoms. So that's like adding carbon between the holes of iron atoms to make carbon steel. And actually carbon steel is taking steel itself, which is an alloy, and then adding the carbon to it to kind of just give it some more strength. That is everything I have for you on ionic and metallic bonds and ionic and metallic materials. If you have any questions, you should know how to contact me, so go right ahead. And other than that, guys, take it easy, stay safe, and stay healthy.